And then this way the caption will appear. Okay. Today's our penultimate class before next week's exam. I should have a draft of the exam made by today, so we'll talk a little bit more about what your exam is going to look like tomorrow during our lab. Tomorrow's lab is a dry lab workshop based around today's topic. Of course, as always, I'll go through a couple questions with the class before I give you your worksheet, but I will be talking a little bit about your exam, the structure, what to expect, and I'll also carry for you the formula sheet that you'll be provided as part of the exam. So be sure to show up to lab tomorrow on time because, of course, labs are not recorded and you wouldn't want to miss any important details related to the exam. Jumping into today's new topic, we are talking about chemical equilibria. Now, to understand what exactly equilibria is, let's kind of think back to last week's topic when we covered kinetics. Way back when we covered kinetics, one of the first things I had drawn for you, or at least provided, was a graph that looks a lot like this, where on the x-axis is time, and on the y-axis is concentration. If you recall, what I had told you last week was at the very start of the reaction, we expect high amounts of reactants. At the very start of the reaction, we expect very low amounts of product. Of course, at the very split second that it starts, we expect there to be zero product, but we're drawing it on the graph like this just to get the point across. Over the course of the reaction, however, the reactants are expected to decrease. Over the course of the reaction, the products are expected to increase such that by the time the reaction is over, in an ideal world, we'd have 100% product and 0% reactant. This is what I taught you last week. This is the expected graph in an ideal world. Now, between you and me, I kind of lied. The graph doesn't actually look like this. In fact, although a lot of the pieces are the same, the x-axis being some unit of time, the y-axis being some concentration. And yes, technically speaking, what is still true is at the very beginning of the reaction, we should have nothing but reactant. And at the very beginning of the reaction, we should have effectively no product. Now, up to this point, everything so far from last week is true. But the difference, of course, comes into how I draw the graph. In fact, we don't actually see that nice linear slope in either direction, positive or negative. In fact, what we see is something like this. A curve where the reactants and products do not cross, but they do meet. In other words, what we actually see is a slightly curved gradient. And although it is still in line with expectations, reactants do clearly decrease, products do clearly increase. The truth is that they kind of meet somewhere in the middle, such that you can say that you have 50% reactants and 50% product. In other words, it's quite often rare to have a situation where you end up with that nice, clear 100% product, 0% reactant. This phenomena, where they end up meeting, is what's known as equilibrium. Equilibrium is a term given to describe this phenomenon where the concentrations of reactants and products do eventually meet. We can give it a much more formal description as follows. Chemical equilibrium is established when the rate of formation of products is equal to the rate of formation of reactants. Now, first thing, please notice that although I do use that phrase rate of formation twice, they are referring to different things. Rate of formation of products versus rate of formation of reactants. What exactly does this mean? Well, the term rate kind of implies there's some speed behind it. Of course, we talk about how reactions take place over the course of time. What we actually have occurring is, of course, what we know as a dynamic equilibrium. And what that means is for a generic reaction where A is converted to B, the reaction is reversible. And reversibility is represented by this arrow right here. If you recall, we had seen this arrow earlier in acids and bases back when we were identifying conjugate acid, conjugate base, and all the like. And way back when I told you, don't worry too much about what that arrow means. We'll come up on it later. We're now here. This arrow indicates that a reaction is reversible. That is, it can occur in the forward direction. It can also occur in the reverse direction. Now, to understand reversibility, think about something like ice melting. We know, of course, that ice can melt into a liquid water. That's one direction. But at the appropriate temperature, we can actually freeze the liquid water back into ice. So when we say something is reversible, we literally mean it can occur in both directions. Ice will melt, turn into liquid, and the liquid can freeze to return to ice. So the concept of reversibility just means both directions are possible. But how exactly does that explain or help us understand what equilibrium is? Let's look at a sample reaction. For example, the conversion of N2O4 to 2NO2. Also, a reversible reaction. Remember what reversible means? It means that it can go in the forward direction, it can break down, and it can go in the reverse direction, combining to reform your reactant. Equilibrium is established when the rate of the forward is equal to the rate of the reverse. But what exactly does this mean physically? How can we observe this? Well, we can't observe it physically, meaning there are no visual cues to tell us something is at equilibrium. But I actually like to think about a specific example. I actually like to think about tug of war. Now, if you've ever watched the first season of Squid Game, if you've ever watched Boys Play at the Beach, you know what I'm talking about when I say tug of war. You have a rope in the middle. You have teams on opposite sides. It's effectively a contest of strength. Pull the other team, pull the other person over to your side. Basic idea is laid out. But let's think about a specific scenario of tug of war. Let's say that on opposite sides of the rope, you have teams, and these teams are evenly matched in terms of strength. If they're evenly matched in terms of strength, is that rope going to go to either side? No, not really. I mean, yeah, it might shake a little bit, but if both sides are equal and matched, there is no clear winner. That rope is effectively perfectly still. But you and I both know that in the game of tug of war, both sides are pulling with as much strength as possible. It's just that both sides are pulling of a similar strength while the rope isn't moving. So in the same way, I want you to think about equilibrium. Equilibrium is established because both directions are pulling, but they're pulling at the same rate such that no side is clearly winning. We know that a reaction is happening, but they're occurring at the same rate such that we don't see a clear difference. So since we can't quite see chemicals in a beaker or flask pulling on a rope, how do we know if a reaction is at equilibrium? Well, here's where we introduce some math. We will calculate what's known as the reaction quotient. This is given the symbol Q sub C, reaction quotient. To calculate the reaction quotient, we must first need a fully balanced equation, here generically shown as A plus B gives us D plus E, where the capital letters are meant to represent the chemical compounds, and the lowercase letters are meant to represent their stoichiometry. There's those big numbers in front. The reaction quotient QC is equal to the concentration of the products divided by the concentration of the reactants, where the concentrations are raised to the stoichiometric value of the products and reactants. What does this mean in the case of this generic reaction? Well, like I said, we're going to have the products on top, in this case, D and E. We're going to have the reactants on the bottom, in this case, A and B, raised to the power of their stoichiometric coefficients, in this case, the lowercase a, b, d, and e. So in theory, and in actuality, the only thing we really need to calculate the reaction quotient, or the only two things, are a balanced equation and the specific concentrations of the chemicals involved. Thinking back to that one example we just did, the breakdown of N2O4 into 2NO2, the reaction quotient is equal to the product, NO2, divided by the reactant, N2O4, raised to the powers of their stoichiometric values. Where, of course, I got the 2 here, because there is a 2 in front of the NO2. It's implied to be a 1 in front of the N2O4. So the power would be 1. And between you and I, we all know that anything raised to the 1 is itself. So we don't need to specifically write that number. And this is the equation we would use to calculate the reaction quotient. All we, of course, need is the concentrations. But this is just a calculation of something called a reaction quotient. How do we use this information to tell us if something is at equilibrium? Well, the first thing to note is at a given temperature, every reaction will have what's known as an equilibrium constant. This is given the symbol K subscript EQ, equilibrium constant. Your textbook or some online resources may refer to it as KC. They're interchangeable. I will prefer using the KEQ. You all know how much I like using those subscripts as labels. It'd be easier for me to read them. Now, if every reaction has an equilibrium constant, to determine if a reaction is at equilibrium, you have to compare the reaction quotient to the equilibrium constant. When you compare the two values, there are three possible outcomes. The first outcome, the simplest one, is if the reaction quotient is equal to the equilibrium constant. In this case, the reaction is set to be at equilibrium. So if the number you calculate matches the constant, then the reaction is at equilibrium. If the reaction quotient is less than the equilibrium constant, then you are not at equilibrium. And what you will do is you will favor the products to establish equilibrium. All right, so here's a little new phrase, will favor the products to establish equilibrium. We don't know exactly what that phrase means just yet, but we know that if QC is less than KQ, then it is not at equilibrium. The other option is if the calculated quotient is greater than KEQ. If it is greater, you are again not at equilibrium. And this time, you will actually favor the reactants to establish equilibrium. Again, we don't know exactly what that means to favor. We'll talk about that in just a few moments. So to determine if a reaction is at equilibrium, we calculate the quotient, the QC. All we need to calculate it is the balanced equation and, of course, any concentrations. And then we compare the two. If the calculated value is equal to KEQ, then you're at equilibrium. If it's not equal, then you're not at equilibrium. So let's see a sample question. This is the reaction that shows the decomposition of SO3 into 2SO2 and O2. I'm going to go ahead and tell you that the equilibrium constant for this reaction is 0.1. The equilibrium constant is unitless, so it is just a number. The question reads, at 3:50 p.m., the concentrations are as follows. SO3 is equal to 0.5 molarity. SO2 is equal to 0.2 molarity. And O2 is equal to 0.1 molarity. The question simply asks, is the reaction at equilibrium? I've just shortened equilibrium since I ran out of space. But is the reaction at equilibrium? Okay, so we know that ultimately to answer that question, what we will be doing is we will be comparing QC to KEQ. We already have the equilibrium constant. We can calculate the QC. QC is equal to the products, SO2 times O2. The products divided by the reactants, which in this case is just the one SO3, raised to the power of their stoichiometric values. There is a 2 in front of the SO2, so it gets squared. There's a 2 in front of the SO3, so it gets squared. Implied to be a 1 in front of the O2, anything raised to the 1 is itself. With that, we can plug in our values. 0.2 squared times 0.1 all over 0.5 squared. We're going to go ahead and put this in our calculator. 0.2 squared times 0.1 divided by 0.5 squared. The answer I see here on my calculator is 0.016. Is this number equal to KEQ? Not even slightly. Not even closely. Not even round up. It's not equal at all. QC is not equal to KEQ. Therefore, this reaction is not at equilibrium. Now, in the question, I went so far as to specify the time. I said at 3:50. Now, of course, this, the specific number is all too unimportant. But the point I'm trying to make is it's at a specific moment. You have to evaluate what's going on at that moment. At 3:50, the reaction is not at equilibrium, but that might change. Maybe at 4:20, it goes through equilibrium. Maybe even at 10 p.m. at night, it's still not at equilibrium. You see, the thing about equilibrium is every reaction wants to be at equilibrium. That's that dynamic equilibrium we're talking about, that state where the rates are the same. It's nice and stable. So the next question is, what direction will the reaction favor / shift towards to establish equilibrium? You see, at 3:50 p.m., we have deduced the reaction is not at equilibrium. Well, guess what? The reaction wants to be. So it's going to have to do something to get to equilibrium. Remember, what is equilibrium? It means that the rates are equal. If you're not at equilibrium, the rates are not equal. We want to get to that point of equal. There are two ways to figure this out. Both methods work. Whichever method you use, this depends on your comfort. Starting with method A. Method A is the simpler one. It just recalls you to remember what are the different possibilities. In other words, depending on Kc being less than or greater than, well, let's take a second to look at the numbers. 0.001 versus 0.1. Of course, we should be able to tell pretty quickly this is a case where Qc is less. So, of course, you could just memorize the rule. In this case, when Qc is not at KEQ, it is not at equilibrium. We've already established that, but it will favor the products to establish equilibrium. That means that to get to equilibrium, the products need to win such that they're at an equal strength, an equal speed. The other way we say this is that it will shift right. Where does that shift right come from? Well, remember how a reaction is read. You can either go in the forward direction, aka to the right, or you can go in the reverse direction to the left. So what are we saying? Let's say that one more time. Let's say at 3:50 p.m., guess what? The reaction is not at equilibrium. To get to equilibrium, the products have to win. That means we need to shift right. The products will be favored. The other way you could have deduced this is a visual trick I like, which is you draw a scale from negative infinity to positive infinity. Smack dab in the center, you write your equilibrium constant. In this case, it's 0.1. And to the best of your abilities, put on the scale where your QC is. Remember, we've already established it's less than. So it's going to be over on this side. It doesn't really matter where you put it. Just arbitrarily put it somewhere. QC, 0.016. The reason I like this is because it shows me visually that to get to KEQ, I have to shift to the right. You can either write the sentence, you can write the phrase, or you can just draw the arrow. All three of these tell me the same thing. To establish equilibrium, we're going to favor the right-hand side, the product side. Do we have any questions so far? Okay. There are two rules to using QC. The first rule is no solids or liquids are included in any calculations or conversations. The simple reason for this is that solids and liquids, their behavior when it comes to equilibria is a bit too complicated for a general chemistry class. This is something you would learn if you were to go on and take inorganic chemistry, which is a course you take after organic. That one's typically an elective. So unless you plan on being a chem major or something along those lines, it's unlikely that you'll ever end up taking inorganic chemistry. We do not include solids or liquids at this level simply because their chemistry is too complicated. It's easier to just ignore them in their entirety. We only include gases and aqueous species. No solids or liquids. We're going to ignore them. They may be written as part of the reaction, but they're not going to be included in any calculations or conversations. Let's see what that looks like. Here's another question. Here we have the breakdown of carbon monoxide into solid carbon and carbon dioxide. I'm telling you that the equilibrium value is 7.7. And here's what the question reads. It reads, oops. At 9:02 a.m., the concentrations are as follows. CO is 0.34 molar. CO2 is 3.6 molar. Is the reaction at equilibrium? And if not, which direction will be favored to establish equilibrium? So obviously, this is a two-part question. Is it at equilibrium? And then if not, which direction? We're just putting it into just one single written question. To determine if this is at equilibrium, the first thing we have to do is calculate the reaction quotient. The reaction quotient is equal to the products divided by the reactants raised to their stoichiometric values. You should immediately notice that I'm missing one product. Recognize, of course, that one product, carbon, is a solid. Solids are not included in our conversations or calculations. The other way you could have remembered that is, I did not give you any information about the solid carbon. I only gave you concentrations for the two gases. The end result is the same. We do not include solids in our conversations. We can now plug in our values. CO2 is 3.6. CO is 0.34, which will be squared. If we put this on our calculator, 3.6 divided by 0.34 squared looks like we get 31.14. Does it really matter how many decimal places? I mean, ultimately, all we're doing is comparing it to our equilibrium constant, and we should pretty quickly see doesn't match at all. Serenity is out of hand. I can't quite hear you. Maybe I just need to get a little closer. Could you repeat your question? Oh, scroll up. Okay, yeah. Just a little bit. Okay. So we went ahead and calculated the reaction. I'm sorry, we went ahead and calculated the reaction quotient. And we very quickly recognize, okay, yeah, this is not at all equal to the equilibrium constant. That should be very obvious. We're just comparing the two numbers, 7.7 versus 31. Not at all equal, not at equilibrium. Go ahead and write it if you want to make it absolutely clear, not at equilibrium. So the follow-up is now, what direction will be favored to establish equilibrium? As I mentioned, I really like that visual tool I used, which is drawing a scale from negative infinity to positive infinity. Smack dab in the center, I'm going to write my KEQ, which is 7.7. Then I'm going to write my QC, arbitrarily. I know it's going to be bigger. I know it's on the right. 31.14. The tool tells me visually, beyond a doubt, to get to equilibrium, we're going to favor the left. In other words, we are going to favor the reactants. You can also say that it will shift left. And of course, just writing the arrow also works. 3 different ways to tell me the exact same answer. Again, think about what this means about the reaction. This reaction at 9:02 in the morning has the following concentrations, and it's not at equilibrium. It wants to get to equilibrium. So who's got to win? The reactants. We shift left. We have to make more reactant to get to equilibrium. We need to know a couple of things about KEQ. Number one, I've already pointed this out, but let's make sure it's written somewhere. KEQ is unitless. It is simply a number. It is a constant for the reaction at hand. KEQ does not indicate speed. In other words, what I'm saying is just because a reaction has a large KEQ does not mean that it is a fast reaction. Similarly, a reaction with a small KEQ does not mean it is slow. If it happens to be, that's just a coincidence. But the two do not directly correlate with one another. How do we know about speed? Well, that's kinetics. That's another topic we went over in the last few weeks. KEQ is temperature dependent. Meaning the same reaction can have different equilibrium constants at different temperatures. Of course, You are led to assume that without specified otherwise, at least on an exam, on a written question, all reactions take place at room temperature. But if I do want to specify a different temperature, I would. Lastly, most reactions in this world are reversible. So more often than not, I would probably say more than 90% of reactions in the world are reversible. Remember, what does reversibility mean? It means it can go in both directions. We talked first about the example of ice melting. We're not saying that ice melts fast. We're not saying it melts slow. We're just saying it's reversible. You can melt ice. You can freeze water. You can boil water, turn into a gas. You can condense the gas, get back your liquid water. Most reactions are reversible. Actually, only a very few that aren't. One example of an irreversible is the burning of a matchstick. Once you burn that matchstick, you can't quite get that matchstick back. That's an example of an irreversible reaction. Let's now move on to our next topic under Equilibria. Le Chatelier's principle. Oh, that's really close to the top text. Le Chatelier's principle states that if a reaction at equilibrium is stressed, the reaction will shift / favor one side to relieve that stress reestablishing equilibrium. Le Chatelier's principle is loosely, and I mean very loosely, based around one of Newton's laws. For every action, there is an equal but opposite reaction. In other words, if a reaction is disturbed, if a reaction is stressed, the reaction, pardon a pun, reacts predictably. Remember, I talked about how every reaction wants to be at equilibrium. So when at equilibrium, if it gets stressed, it wants to reestablish equilibrium. So it will shift or favor one side to relieve that stress. We've actually already seen this quantitatively. I told you at specific time points, blah, blah, blah. The concentration is blah, blah, blah. Le Chatelier's principle is more of a qualitative topic. Let's see what that looks like. I'm going to draw a table. This table looks like 3 columns and 7 rows. I'm going to write it up there so you can draw it yourself. But this is going to be 3 columns, 7 rows. The column headings are as follows. If the reaction will shift. And finally, because the system. Strange title for column headings, but you'll see the vision in a bit. Okay. Le Chatelier's principle is a qualitative thought experiment, basically. It allows us to make predictions based on purposeful changes. For example, if we add some reactant or product, so the reaction is already at equilibrium, and we say we're going to throw in some more reactants. If we stress the system by adding a reactant or product, the reaction will shift away from that reactant or product. So here's how we start reading the table. So we start, if we add reactant or product, the reaction will shift away from reactant or product because the system consumes the excess reactant or product. So the table is meant to be read as a full run-on sentence, where the column headings are just the consistent phrases. So think about what we're saying here. We're saying that the reaction is already at equilibrium, and we decide we're going to just throw in some more reactant, just for the hell of it. By throwing in some reactant, we have disturbed the equilibrium. To get back to equilibrium, the reaction says, hey, I got to get rid of some of this reactant that this guy threw in. I got to use it up. I got to shift away from that reactant. So what happens if we remove a reactant or product? Well, if we remove some reactant or product, the reaction will shift towards that reactant or product. So the reaction's at equilibrium, and we decide I'm going to be my worst villain. I'm going to go in that beaker. I'm going to take out some of that product, and I'm going to say, I don't care. The reaction says, why would you do that? Now I've lost some product. I got to shift towards that product. Why? Because I have to replace what was lost. That's adding and removing reactant and product. Another way that we can switch up a reaction or stress a reaction is we can increase pressure. If we increase pressure, the reaction will shift towards fewer gases. The reason it does that is that we reduce the total volume overall. This is based on Boyle's law, P1V1 equal P2V2. Of course, you don't need to know gas laws for this upcoming exam, but you should understand why an increase in pressure would want a decrease in volume. If we decrease pressure, we will shift towards more gases where it would just be the opposite reason. We want to increase the total volume. That's pressure. The other thing that we can do to stress a reaction is we can increase temperature. If we increase temperature, the reaction will shift towards the endo direction, where, of course, we know from our thermodynamics chapter that an endothermic reaction is one with a positive energy. When it says positive endo, what does that mean? It means energy enters. Don't forget that the positive and negative refer to direction. The reason why this happens is that we want to absorb that extra heat. We can also decrease temperature. When we decrease temperature, we will instead favor the exo direction, where exo is, of course, the negative energy value. That's where energy exits. And the reason for that is that it produces heat. These are the guiding principles that Le Chatelier bestowed upon us. Take one and pass it down. Take one and pass it down. Take one, pass it down. Take one, pass it down. All right, a handout's coming everyone's way. Here. Does everyone have a copy? You didn't get a copy? You just need one more? Okay. All right, the handout that I just passed out is a virtual carbon copy of the table I have up on the board, just presented in a typed format. You will not be given this handout as part of your exam. In other words, I am expecting you to memorize this table because I will be asking you to utilize it to predict certain reactions, to predict equilibria. Again, you will not be given this table on your next exam. I do expect you to memorize it. This is just a carbon copy of the table I just put up on the board and we went through together. Let's try to understand now the utility of Le Chatelier's principle. We're going to look at an application of Le Chatelier's that's used even to this day. We're specifically looking at what's known as the Haber-Bosch process. The Haber-Bosch process is the following reaction. It is a combination of N2 gas and hydrogen to form NH3, aka ammonia. I'm also going to go ahead and tell you that the delta H for this reaction is negative 92.2 kilojoules per mole. I want to make something clear. I'm not expecting you to memorize specifics about the Haber-Bosch process. We're just looking at an example in the real world as to how Le Chatelier's principle can be used. The following reaction, the Haber-Bosch process, represents one of the most simplest reactions known to man that takes from the natural atmosphere nitrogen and hydrogen to make ammonia, NH3. Now, I really shouldn't have to explain the benefits and utility of ammonia, so it should be clear why this reaction is so important, or rather so famous, for its simplicity. Ammonia has a broad variety of uses in a wide variety of cases, not to example, just for example, bleach. As a result, the Haber-Bosch process is one of the most commonly performed reactions across teaching labs, research labs, as well as in industrial plants. In other words, what I'm trying to say is that it's more often than not cheaper and more efficient for these companies to make ammonia themselves than try to purchase it from some third-party supplier. This represents one of the most fundamental reactions in all of industry that chemical synthesis is involved. And its simplicity is what makes it so gosh darn efficient. Here's how we would use Le Chatelier's principle to maximize efficiency. So to maximize the efficiency of this reaction, when we say maximize efficiency, what that literally means is we want to favor the product side. And I'm just going to put an arrow to the right. I mean, think about it. You're a big time investor in this company, and they're telling you, okay, we're going to spend $30 million on the Haber-Bosch process. Your first thought is my money being put to good use? Are you making the most of my money? How do we go that? Well, I want a lot of ammonia. I'm paying you, I'm investing in you to make ammonia. What can you tell me that you can do to maximize making ammonia, making NH3? So you go back to your General Chemistry 1 notebook, and you say, all right, let me just take a real good long look at this reaction. I can see from the energy of the reaction that this is an exothermic reaction. We just did thermochemistry in the last couple of weeks. We read from left to right. This is what tells us it is exo to the right. All right, so you look and you say, all right, well, okay, I know that the energy of the reaction, I can see that to the right is exothermic. And I go back and I say, okay, I know that if energy is involved, I can look at temperature. I want to favor the right. I want to favor the exothermic direction. Do I increase or decrease temperature? Decrease. Guess what is actually done? This reaction is performed at incredibly low temperatures. If we decrease the temperature, aka run it at a colder temperature, what we end up doing is that we favor that exo direction. So you go back to the investor and you say, Mr. Investor, you want to maximize ammonia production, tell you what you do. You lower the temperature. Investor says, where'd you come from this logic? And you work him through, you guide him through Le Chatelier's principle, and you explain the concept. You talk about Squid Games and tug of war to get the point across. And he stops you halfway through and says, but wait a second. There are gases in this reaction. N2, H2, NH3. They're all gases. I swear to God, there's something about Le Chatelier's that tells us we can favor the side with fewer or more gases. Okay, so now the question comes up, which side is fewer, which side is more? All right, so you go back and you say, all right, let's take a second, let's count. On the right-hand side, I can clearly see that there are 2 gases in total. I know this because there is an NH3 and the stoichiometry tells me that there are 2 in total. That is on the product side. On the reactant side, I see I have 1 N2 and 3 hydrogens. So how many gases in total do I have on the left? 4. Where did that 4 come from? I have 3 hydrogens as well as the 1 nitrogen. I have 4 gases on the left. So now you say, all right, this tells me that the side with ammonia has fewer 2 gases. The side with the reactants has more. And you say, well, what did the investor want me to do? The investor wanted me to favor the right. It wanted me to favor the ammonia. It wants me to favor the fewer. Looking at Le Chatelier's principle, to favor fewer gases, what do I do? Do I increase or decrease pressure? One more time, someone shout it out. Increase pressure. Guess what? This reaction is performed at incredibly high pressures. At high pressures, we favor the side with fewer. That favors the right. And you go back to Mr. Investor and you say, please, sir, that's enough. I don't think we can maximize it anymore. And he says, but wait, there's more. Wasn't there a whole category on top that we missed? Investor points out, well, thank God you taught me about Squid Games and tug of war, because otherwise, how else would I know if I want to go towards a product? What do I got to do? I got to remove that product. Investor says, look, I'm giving you a lot of money. You tell me you can't do this? I say, yes, I can. So guess what? In industry, due to money and investments and, of course, various equipments, the ammonia is continuously removed. The way they have the whole plant set up is that as they're making the ammonia, they're collecting it. So they're continually removing the ammonia. It's as if though you let the reaction take place in the beaker, and as you saw the gas coming up, you grab it with your hand and you throw it away. You don't actually grab it. You don't actually throw it away. They have nice fancy equipment to collect it and all that nice stuff. But by continually removing the ammonia, by continually removing a product, we favor the product. And this is the utility and beauty of Le Chatelier's principle. Using very simple qualitative trends, we're able to carry out reactions to maximize efficiency. We looked at this reaction, we analyzed this reaction, and we said based on various factors, it was exo to the right to favor exo, we take place at very low temperatures. We said based on gases, if we wanted to make more product, we do this at high pressure. And of course, the last thing we can do is through money and various nice fancy equipment, we continually remove the product. In doing so, we favor the product. Do we have any questions? With that, we will officially end Module Exam 4 content. Tomorrow's lab workshop is entirely dependent on today's material. Please be sure to carry back your calculator as well as the handout. Since we've officially ended this new module content, I will post my notes with tonight's lecture recording when I get home. We'll end class for today. If you have any questions, come talk to me now. Otherwise, I'll see you all tomorrow for lab. Don't forget, I'll be talking about the exam at the start of lab, so please show up early. Have a good day. Dry lab. It's a workshop.